Okay, for part C, I'm kind of trying to cover up the diagram I drew of the figure in the textbook we just saw. Uh, I drew it with four waves and it came out absolutely awful. So just pretend you didn't even see that. Um, what we just saw in the diagram from the textbook is de Broglie's theory was that um, electrons, in addition to particles, also take the form of standing waves, and that each orbit within an atom allows a certain number of waves, but it has to be a whole number of waves. So that's why the involvement of the integers in all the equations, the 1, 2, 3, 4, that kind of thing. And the example we saw from the textbook had six entire waves around the atom. So that particular orbit would presumably be n equals 6. So the de Broglie condition is given as 2 pi r being the circumference of a circle, like an orbit, for instance, is equal to n times lambda, n being, and again, an integer, 1, 2, 3, 4, 5, 6, and so on. So n times the wavelength of that standing wave that corresponds to the electron. It turns out that a few years later, scientists, different scientists observed interference patterns for electrons that they were shooting through crystals. Crystalline substances similar to sodium chloride, where you have a regular repeating arrangement of atoms or ions, and they're sort of stacked up in rows on top of each other. And it turned out that the rows of atoms or ions in these crystals were acting sort of like slits that light goes through and creates when it creates interference patterns. So electrons could be shot through these crystals and would emerge with interference patterns also. And again, that's something that shouldn't happen for something that's purely a particle. It's something that should only happen with waves or things with significant wave-like properties. And so that sort of confirmed that electrons do indeed have significant wave properties. So the spacing between the layers in the crystals ended up being about the same as the de Broglie wavelength of the electrons, and so you got an interference pattern. And again, that means the electrons are governed by wave equations, not by traditional Newton's equations. For calculating de Broglie wavelengths, we can use the equation lambda equals h over mv. And again, that can be used to calculate the wavelength for any, or the de Broglie wavelength, that is the matter wavelength, for any object that's in motion. It's usually used for small objects like electrons and atoms, or maybe ions, that kind of thing. But it can be used for larger objects too. In real life, things would get a little more complicated than that. But you can actually calculate and at least get an idea of what the matter or the de Broglie wavelength would be for really large objects in motion, like in this example, a softball. A softball is an object in motion, and obviously any object in motion has a certain energy associated with it, kinetic energy if no other kind. And kinetic energy is 1/2 mv squared, m being the mass and v being the velocity. So the two requirements for having energy would be mass and velocity. So any object that has those two things would have energy associated with it. And according to de Broglie's theory, anything that has energy associated with it should have a wave associated with it also. And you can calculate the wavelength now using de Broglie's equation. So calculating the de Broglie wavelength of a softball of mass 100 grams traveling at 35 meters per second, if it can be considered a single particle, which technically it can't, but if it could, then the de Broglie wavelength would be h over mv. So that's 6.626 times 10 to the minus 34 joule seconds. That's the Planck constant. Divided by the mass. Remember, the mass has to be in kilograms. So 100 grams becomes 0.1 kilogram. And and the velocity is 35 meters per second. Those are the units we want for velocities, so we can leave that the way it is. And the matter wavelength ends up being 1.89 times 10 to the minus 34 meters. Now, if you think about it, the shortest wavelength of electromagnetic radiation for something like gamma radiation would be about 10 to the minus 20 meters. This is way, 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 way shorter than that, meaning that this softball traveling at 35 meters per second has an energy that's way, 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 way bigger than the energy of one photon of gamma radiation. Now, the thing about gamma radiation is you have to remember that the 10 to the minus 20 is the wavelength of one particular photon of gamma radiation. Anytime you have a source of gamma radiation, it's probably giving out a whole lot of photons. And so that would be something to worry about once, the collective effect of all of those photons. But any one of those photons actually wouldn't have all that much energy. And in fact, it would have a minuscule energy compared to this one softball. You can go even bigger if you really want to. You can calculate the, say, the de Broglie wavelength for a 3,000-pound car traveling at 65 miles per hour. Of course, sorry, the catch here is that you have to convert the weight to kilograms. So if you remember how to do it, you can use a conversion factor, like the fact that there's 1 kilogram for every 2.2 pounds. You want pounds to cancel, so pounds should go on the bottom in the conversion factor. And so 3,000 pounds times 1 kilogram over 2.2 pounds tells us the mass is 1,364 kilograms. And for the velocity, you're going to have to change 65 miles per hour to meters per second. So 65 miles per hour. Remember, when we convert compound units like this, and in other words, something where we have one term with two units that both need to be converted, the best approach to it is to convert one unit at a time. So first we can convert miles to meters, and then we come back and do hours to seconds. So just ignoring the hours for the moment, 65 miles, and there's 1.61 kilometers per mile. So now miles cancel out. And we have kilometers per hour if we want that, but that's not what we want. So we have to go to meters for the distance. And there's 1,000 meters per kilometer. So now kilometers cancel out, and we have meters as the unit in the numerator, which is what we want. And the problem is that we've still got hours in the denominator at this point. So we have to change the unit in the denominator to seconds. We know there's 1 hour for every 3,600 seconds. Hours in this case goes on top, so that it'll cancel with hours on the bottom back here. And we want seconds on the bottom, so that's where the 3,600 seconds go. So now if you take 65 times 1.61 times 1,000 divided by 3,600, you get 29.07 meters per second. So that's your velocity in meters per second. Now you can put that into the de Broglie equation as h over mv. H, again, being Planck's constant, 6.626 times 10 to the minus 34 joule seconds. The mass being 1,364 kilograms, and the velocity being 29.07 meters per second. When you multiply all of that out, you end up with a wavelength of 1.67 times 10 to the minus 38 meters. So 10 to the 38th is even smaller than 10 to the minus 34. Sorry, 10 to the minus 38 is even smaller than 10 to the minus 34, which is appropriate because, of course, a 3,000-pound car traveling down the road at 65 miles per hour has a whole lot more energy than a softball traveling at 35 meters per second. Even though the softball was actually traveling faster than the car, the softball is a lot smaller and a lot lighter, so it has less energy overall than the car does. And so 10 to the minus 38, that's almost an unbelievably short wavelength. And we don't even actually have the means to measure wavelengths that short. We can only basically get it through calculation. Now, of course, in real life, as I said with the baseball, a car really doesn't qualify as a single particle under the de Broglie theory. So this is really only kind of hypothetical. If you had a single particle that was the size and mass of the car that was traveling at 65 miles an hour, then that's what its matter wavelength would be. Next came along Werner Heisenberg. And if the name Heisenberg rings a bell, there may be some Breaking Bad fans in the audience. That's the name Walter White. Although you guys may be too young to have watched that. It's been off the air for a while now. Heisenberg is the name Walter White adopted because of its association with uncertainty. Kind of ironic, though, as Walter White was a chemist and Heisenberg was a physicist. But anyway, he's a physicist whose work borders on chemistry. So we'll let it go. He determined the limits of the accuracy with which we can actually know the properties of particles at very small scales. Things like photons and electrons, for instance, especially electrons. That's what he was concerned with, because he was concerned with the structure of the atoms, particularly with the arrangement of the electrons in an atom. And what he found was that the more accurately you know the momentum, that is the mass and velocity, the less accurately you would know the position of something, and vice versa. So in other words, the Heisenberg uncertainty principle means that it's not possible to know both the momentum and the position of a particle accurately at the same time. You can know one accurately and the other not accurately, but you can never know both of them accurately at the same time. Part of it is due to the idea that observing something can change it, can change its behavior. And it seems like an odd concept at first. I mean, certainly if a person knows that they're being watched, they might behave differently than they would if they know they're not being watched. But even for strictly physical processes like a rock rolling down a hill, what difference does it make if somebody's looking at it or not looking at it, And that's true on macroscopic scales. Whether you're looking at it or not doesn't matter. Whether the sun is shining at it or not barely matters, doesn't matter to any significant extent. But when you get down to tiny little levels, like positions of electrons in atoms, in order to observe something like that, you have to probe the atom with some sort of probe, like, for instance, light. And electrons are so small and so lightweight, that is lacking in mass, that even hitting them with a stream of photons, in other words, light, so that you can look at it, would alter the position of the electrons. And of course, electrons are too small for us to look at with the naked eye, so you would have to use something like, say, X-rays or maybe other electrons to determine the position of the electrons, and that would have even a greater effect on the position of the electron. So you can't really find the position of the electron without changing the position of the electron. And so that's kind of what Heisenberg was getting at. So the uncertainty of momentum versus the uncertainty in location are kind of inversely proportional. The better you know one, the less you know the other. In practice, we generally know the momentum of an electron in an atom pretty accurately. So when it comes right down to it, in real life, it's the position of the electron where the uncertainty comes in. The uncertainty in position would be called delta X. That's sort of like variation in position or the changeability of position. And the uncertainty in the momentum would be termed delta P sub X. P is the physics symbol for momentum, and the equation is just P equals mv, mass times velocity. And the subscript X just means that we're talking about momentum in the X direction. If we're looking at like what is the position in the X direction, then we'd have to be considering speed and mass in the X direction also. And this in practice is due to the uncertainty in velocity, which is delta V sub x. That is the uncertainty in velocity in the x direction. We know the mass of electrons with great accuracy, and so any uncertainty in momentum would be due to the uncertainty in the velocity rather than the mass. And Heisenberg determined that the uncertainty in position times the uncertainty in momentum, which can also be represented as delta x times m delta v. That is, m is just written as m because, as I said, we know m very accurately, and it's the velocity that there might be some uncertainty about. So m is just called m because there's practically no uncertainty in that, but there is some uncertainty in velocity. So that's delta vx. So uncertainty in position times the mass times the uncertainty in velocity will be at least h over 4 pi in its mathematical value, greater than or equal to. So h over 4 pi gives the minimum value in the uncertainty of the position times the uncertainty in the momentum. The book calls this h bar over 2. But h bar is just h over 2 pi. So I thought it's really simpler just to use the stuff that we've already seen, like h, which is just Planck's constant, over 4 pi. This is just as easy. I don't know why they did that. But you can do it either way, whichever way makes more sense to you. They both work. So this equation basically gives the limit of how accurately we can possibly know position and momentum at the same time for any object, not just electrons, but electrons are what we're most interested in. And like I said, in practice, we know the momentum of electrons pretty accurately. And so the real uncertainty comes in the position. So that's what we normally want to solve the equation for, is the uncertainty in position. An example of actually doing that can be given as if, for example, the uncertainty in the velocity of an electron is about 1%, which is a reasonable number in the uncertainty of the velocity. And the velocity itself is 1 million meters per second, or 1 times 10 to the 6 meters per second, which is actually pretty typical for the velocity of an electron in an atom. They're very, very small, so they can move at a very, very high rate of speed. And so 1% of 1 times 10 to the 6th is 1 times 10 to the 4th meters per second. So the uncertainty in the velocity would be 1 times 10 to the 4th meters per second. What is the uncertainty of its position? Well, we have the equation where the uncertainty in position times the mass times the uncertainty in velocity is greater than or equal to h over 4 pi. What we want to do is rearrange this equation to find delta x. And that means dividing both sides by m delta v. So delta x is equal to h over 4 pi times m delta v. And this equation here gives us the minimum value for the uncertainty in the position. It's going to be at least what we get from this equation. Okay, so for delta x, we're going to have h, which is Planck's constant, which is 6.626 times 10 to the minus 34 joule seconds, over 4 times pi, 3.1415926, blah, blah, blah. You could put the number 3.14 in, but most modern scientific calculators actually have a key that's marked pi. So you could just take 4 times pi times the mass of an electron, which you can look up. It's a well-known number, 9.11 times 10 to the minus 31 kilograms, times the uncertainty in velocity, which I said was 1% of 10 to the minus, or 1% of 10 to the 6th, which is 1 times 10 to the 4th meters per second. And when you multiply and divide all of that out, you get 5.79 times 10 to the minus 9 meters for the uncertainty in the position of the electron within this particular atom, which seems pretty small. So you say, oh, that's a really small number. So that's a pretty good uncertainty for the position of the electron, because generally, if you want to know something accurately, then the uncertainty in that measurement should be small, and that's a small number. But what you have to take into account is the size of an atom. The size atoms are really small. And in fact, it turns out that atoms typically have a diameter of about 10 to the minus 10 meters, which is actually smaller than the uncertainty of the position of the electron within the atom. So according to Heisenberg's theory, that electron could be anywhere in the atom, or even a little bit outside of it, or even actually quite a bit outside of it, because this is about 10 times the size of the atom itself. So in other words, according to Heisenberg's theory, we basically have no idea where the electrons in the atoms are at any given moment. As we'll see as in the next lecture, we can map out where the electrons are most likely to be at any given moment, but we have absolutely no way of verifying where an electron actually is at any moment. We just can't do that because every time we try, we come out with a range of possible locations that's bigger than the entire atom. So, you know, that's a bit of a problem. But unfortunately, like I said, we're able to map out where the atoms are, or where the electrons are most likely to be. And that, you know, gives us something to work with. Just out of interest, these equations also apply to larger objects too. And so you could find out, you know, what is the uncertainty in the position of my car? So, for example, what is the uncertainty in the position of that 3,000-pound car, which we already found has a mass of 1,364 kilograms, traveling at 65 miles per hour, or 29.1 meters per second, if the uncertainty in velocity is 10%. You know, the typical car speedometer is really only accurate to about 10%. And so it would not be unusual for the uncertainty in velocity in your car, as read by the speedometer, to be around 10%. So we'll take that. That means that delta V, the uncertainty in the velocity, would be 0.1 times 29.1, or 2.91 meters per second. And that would mean the uncertainty in the position of the car would be, again, Planck's constant, 6.626 times 10 to the minus 34 joule seconds, over 4 times pi times 1,364 kilograms, times the uncertainty in the velocity, which is 2.91 meters per second. And that gives us an uncertainty in position of the car of 1.33 times 10 to the minus 39 meters. Okay, I just paused the video and checked my math, and sure enough, I used the incorrect number in doing the math. So actually, the uncertainty in the position of the car comes out to be, at minimum, 1.33 times 10 to the minus 38 meters, because it's 2.91 meters per second for the uncertainty in velocity. So what this is not only a really, really tiny distance, even on a scale of individual atoms, 10 to the minus 38 is really, really tiny. Remember, I said the diameter of a typical atom is about 10 to the minus 10 meters. This is way, way, way smaller than that. And what it tells us is basically the larger the object is, the smaller the uncertainty of its location is. The smaller the object is, the larger the uncertainty of its location is, not just relative to the size of the object, but in absolute terms too. The uncertainty in the location of that electron was a lot bigger than the uncertainty in the location of your car. Okay, so that can become a real problem when you're trying to investigate things like where are the electrons in an atom. Needless to say, turns out they could be anywhere within that atom and anywhere within the 10 atoms next to it, for that matter. So this really imposes limits on our knowledge of things at very small scales. Okay, so I think that's where we can leave it for today, and we'll pick up there with the quantum model of the atom next time. But we're close enough to the end of this lecture that I don't want to get into that yet, because that can get really complicated really fast. So we'll work that out next time. So until then, see you later.